Okay, this is a problem on magnetic fields. It reads, in a research station in Antarctic, a circuit containing a partial loop of wire of radius 5 centimeters lies on a table. A top view of the circuit looking down on the table is shown in figure 1, which I'll show in a minute. A current of 5 amps runs in the current in the direction shown, and other portions of the circuit are far away. You have a bar magnet with magnetic dipole of 1.2 A times meter squared. How far above location A at the center of the loop would you have to hold the bar magnet, and in what orientation so that the net magnetic field at location A would be 0? The net magnetic field at location, the magnitude of the Earth's magnetic field in the Antarctic is about 6 times 10 to the negative 5 Tesla. So this is figure 1. This is looking down on it. And so we know the orientation is that B Earth points out of the page. So it would be pointing out of the page. And B circuit would also be pointing out of the page. And so the bar magnet, we know, must be held with its pole downward into the page to even make a magnetic field into the ground. So that's going to be the orientation. And we know the components of the magnetic field at location A are going to be magnetic field due to the Earth, which was given up here, 6 times 10 to the negative 5 Tesla. And we know that there's no magnetic field due to the wires. It's going to be 0. So in order to find out the magnetic field due to this 3/4 of a loop, we just use the same equation that we would for a regular magnetic field, which is this right here. So we're going to do the origin at the center of the loop, which is where A is, and we're going to say that this R is big R. It's a constant. And so I've drawn another figure over here to reiterate that. So you can see this is the big R. This is R hat in the direction towards A. This is the current going around the loop. So you can see that there's this perpendicular relationship at every location around this loop. If you do DL cross R. And so at all locations, DL is going to be perpendicular to R. So DL cross R hat, which we showed R hat is perpendicular, it's going to be DL sine of 90, which is just going to be DL, because sine of 90 is 1. So that's just going to be this R d theta, because that's going to be the angle from here, going around. In R, it's just the radius from A to the center to the loop. So we use this equation and plug in what we know now. Since it's only 3/4 of a loop, we only are going to integrate from pi over 2 to 2 pi. And we can take out the constants, which are going to be mu naught over 4 pi, that's a constant. We have I R over R squared. That's all going to be a constant because the current's not changing, the radius isn't changing, and we know this distance isn't changing. And this relationship here isn't changing either, r d theta. Well, the angle is going to change. So that stays inside the integral d theta. And so we evaluate that and come up with this for the loop. So then we can just add those two together, and then we know B magnet is going to equal approximately this, which this is the equation for the magnetic field of a magnet. So in order to find Z, the distance, we can just change this equation around to find Z and solve for Z. So 0.13 meters is going to be the distance that you would need to hold the actual